available to us?
Pardon?
Will you be able to make a recording available to us, or will it be up online, or what are you going to do?
Yeah, we will post it online. We will edit the video and send it to you also.
Oh yeah, that's great. Yeah, just in case we do well.
Yes, you will do well, I guess.
Great stuff.
So people are coming. Maybe wait another 1 or 2 minutes if you don't mind.
That's fine.
Yeah, then I'll have the opening and I'll give the speaker to you guys.
I'm going to go on mute.
All right, I think I will start now. So hello, everyone. Welcome to the IEEE Big Data Analytics tutorial section. This is Qiu Shi from Arizona State University. Today, we are honored to have Dr. Stephen Harben and Professor Peter Greenrod to join our talk. The topic of the talk is the electricity data analytics, opportunities and challenges. So the background of this talk will be for the there is a need for the increased monitoring of low voltage networks, and included in this talk, there will be discussions on how smart meter data will drive the new ways to manage customers, how community storage can be used to provide benefits to customers and the network, what are some of the roadblocks to realizing these opportunities, and what are some of the ways that they are trying to help facilitate better use of data and analytics. Here's a brief introduction of both of the speakers. Peter Grindrod received his bachelor degree in mathematics from Bristol and a PhD also in mathematics from the University of Dundee. He is a professor of mathematics with the University of Oxford. He is a former president of the Institute of Mathematics and its Applications. He was the founder of 3 successful analytical companies in sectors such as retail, energy supply, mobile telephone, digital media, and digital marketing. Professor Grindrod was a recipient of the Commander of the British Empire in 2005 for mathematics. He is a member of the Biotechnology and Biological Sciences Research Council, a former member of the Engineering and Physical Sciences Research Council, and a member of the Ministry of the Defense Scientific Advisory Council. Dr. Stephen Harben is a digital and data consultant at Energy Systems Catapult, ESC, and a visiting research fellow at the Mathematical Institute in the University of Oxford, where his research is focused on load forecasting for low voltage energy systems, battery storage, control, and energy analytics. His work at ESC focuses on how to support the energy sector through digital solutions, improving data access, and helping bridge the gap between industry and academia. He has over 10 years of experience in big data and data science and was the academic project manager on £30 million new Thames Valley Vision project. He received his PhD from the University of Reading in the conditioning and preconditioning of variational data assimilation for numerical weather prediction systems. So this tutorial today will be around 60 minutes, and at the end there will be Q&A sections. And during the talk or at any time, you can feel free to send me your questions through the chat box if you have. And yes, that's all. And without further ado, I will give the speaker to both of the speakers. So Steve, Peter, you can start.
Brilliant. Thank you very much for the introduction. So I'll start. It's sort of double header. I'm kind of the warm-up act for Pete later. So yeah, as mentioned in the introduction there, I work as primarily as a digital and data consultant at the Energy Systems Catapult. I'll talk a little bit more about what that is later. But I'm also a visiting research fellow. So this talk will be talking about half of those things we mentioned in the abstract, primarily a lot of the challenges I've faced, sort of mainly through the academic side, but sort of ways we're trying to support the sector through the Energy Systems Catapult. Okay, so I probably won't pass maybe through all these topics, but I might briefly mention in each one of them. So I'll introduce Catapult, as I mentioned, some challenges, but then very much focusing on data challenges. So because these are probably one of the biggest roadblocks to a lot of the analytics that you can try and implement in the real world. Then a little bit about some of the ways we've tried to support that system. Two sort of main things here. One is the Energy Data Task Force, and one is through some data science challenges. And then if I've got time, I'll briefly mention something about data science skills. Okay, so who are we? You may have heard of us. We are a UK part government funded, not for profit. And we were set up by Innovate UK. So we're one of 9 catapults, and we're all focused on different areas which are deemed to be quite important to the UK economy, as is the energy systems, but there's obviously other ones which are focused in different areas, ones that are interested in transport, like in connected places. There's digital catapult, and then there's there's medicine and a whole host of others around the UK. But really what we're trying to do is support innovation in the UK. So we try and offer some support services, that might even be, sort of helping people find funding or write white papers. But often we're trying to bridge that gap across stakeholders in the energy sector. So that will be academics, that'll be industry, and that'll be government. We've grown in size. We're only about 5 years old now, and we're 200 sort of experts now in this area and in various areas. We're mainly based in Birmingham, but we've also got a hub in Derby. So I won't go into too much more details about this, but we've got a lot of capabilities and assets. We do a lot of modeling from sort of in dynamics within a house up to sort of the national level. There's the digital and data team, which is what I'm part of, and that's primarily split into two. There's the data science team, which was my old team, and now I moved into the data systems team, which is focusing on data and digital and trying to help support innovators in that area. And there's a whole host of other things: policy, consumer insights, infrastructure engineering, and that sort of thing. So what I thought I'd do is I frame the challenges, not in general, but more looking at forecasting. This is my sort of expertise, but I think it'd be useful to say that, the problems in that area are ones that are shared across the sector. Okay, so maybe first it's worth saying, what is LV? I know that this has different terms and different meanings depending on where you are. The UK and the US, I think, use different perhaps terms for what is low voltage, but even within the UK, that can change depending on the application or what you're doing. But what I'm really trying to say here is, what is that local level? We're looking at sort of microgrids. We're looking at the primary thing we're interested in is the vast number of applications which are there, and the volatility and the features of that data. Why do we care about this area? Well, there's a huge number of applications. The pictures here are all areas that I've been involved in one way or another, whether at the University of Oxford or at the Catapult. But there's a whole host of others in the box there. New technologies with new control mechanisms like heat pumps and storage devices are allowing much more complicated technologies and operations and require much more complicated algorithms. But there's also long-term scenario plannings. What's going to be the impact, of having so many EVs or heat pumps or solar panels in a small local area. But also electricity markets, they're evolving a lot now, and there's a lot of talk about maybe peer-to-peer trading and much more local energy trading. So, all these things are becoming a lot more important and ubiquitous. But to kind of narrow down even further, to sort of fit the narrative of this, so if you want to go back to an application that we're thinking of, one that I've been involved in a lot is storage control for low voltage networks. So as a simple example, imagine we don't want to break the capacity limit of the cables in the local network. We can store a device earlier in time and then discharge it later so that we stay within those capacity limits. Okay, and just to say, we actually did apply this in an actual trial, the Thames Valley Vision project that was mentioned earlier. That we did apply some real battery storage, and we did manage to run some real trials on that, as well as lots of in silico trials as well. Okay, so what is one of the major difficulties down there? And I think the main aspect of this is the irregularity and the volatility there. So these are 4 individual low voltage feeders. They're different sizes. They've got different numbers of consumers on them, some of different proportions of consumers as well, but the bottom one there is a single commercial consumer, and it's very different from the above ones, which are primarily residential. But even when you have very similar numbers of residential, like you do with the top one and the third one, you can still have a lot of different behavior. As you can see in the third one there, it looks like Christmas is a period when people go away, but not so much on the first one. We're talking about maybe 50 households on a feeder, and you can see the volatility increases rapidly as you go down to sort of an individual consumer. And I think Pete will talk a little bit more about sort of, individuals there. But this means, that what algorithms we need and the accuracy of our forecasts rapidly change as the feeder size changes. If we get a smaller feeder, you often get this sort of power law relationship, which shows as you aggregate the number of households, you get a much expanding and diverse range of errors, relative errors, I should say. But even when you think there's this sort of regularity in there, there's measurable things, the power law doesn't quite always fit the rules as we expect. So here is, these are real feeders on an LV network in Bracknell in the UK. These are 100 different feeders. And although the majority of them do fit this sort of power law relationships, it's clear that LV networks are not simply just aggregates of standard households often. You can see a lot of them are sort of anomalous, or they've sort of deviating from this main area, the main curve. But we can also explain why they are. They all have a very common features about them. These all have overnight storage heaters, which are these sort of heaters which are charged electrically overnight, so they can provide heat during the day. And they're often on different tariffs in the UK. And then you could say, well, how does this translate into actually the storage application we were talking about? And although there is a trend as the forecast does get more accurate, there is a bigger deviation in the amount of peak reduction you can get from that storage device. It's not quite as smooth as the forecasts are. So perhaps choosing a good forecast doesn't necessarily equate to a very effective performance on the application you're doing. There's other things we don't really know, and there's a hell of a lot of research that we need in this area now. What we've got here is we've got sort of national level in the US of temperature versus load versus temperature, and we've got some data from the Thames Valley Vision, which was also looking at an individual feeder. And although there's very different mechanisms involved in here, and of course in the US you have air conditioning, and we don't have in the UK, there's clearly some very strong relationships in the aggregated data on the left, and there's not so much on the right. And I actually chose the right one deliberately, so it was one of the strongest relationships. So that tells you there's a difficulty there. And if you look in this in more details, we also did some research to see how including forecasts into this into our models actually help. And actually we found that including whether it's forecasts, whether it's actuals, actually was detrimental to the forecast accuracy. So that a lot of things we assume are true about our models are not necessarily there. So where the question really comes is, where are we really with the current state of load forecasting as well? And I think the topic throughout this talk for myself here will at least be that there's still a lot of work and research that's required. This was a plot that was done by several experts, Tao Hong, Pierre Pinson, and many others who were experts in load forecasting, and also they set up the global energy forecasting competition. They put their own sort of opinion of where this maturity was in the various areas, and I've circled the short-term load forecasting, which is what I've been essentially talking about. And although they say it's very mature as point forecasting, as probabilistic, which is really essential at the low voltage level to describe the volatility, there hasn't been much work done. The WPF there is one of the more mature, and that's wind forecasting, which a lot of work has been done. And then we've got long-term load forecasting, which is pretty much only probabilistic forecasts. And then the bottom, electricity price forecasting and solar price forecasting. I think things have moved on a bit since this. Obviously, this was 2016. But I did sort of just simple heuristics here, looking at the amount of literature out there in the various areas. And this would confirm that load forecasting is a relatively mature area. But if you look at the literature in terms of low voltage systems or smart meter forecasting, it's very sparse, relatively speaking. But to be a bit more maybe rigorous here, recently I worked on a paper with a few colleagues looking at low voltage forecasting. We did a review of over 200 papers, and we found there was a lot of methodological and scientific problems with these papers, and data problems as well. I mean, one thing which was seen to be very common was that often many of the papers do not use benchmarks, and if they do, they often just use a non-competitive one. So it would essentially just to be saying, you're doing very well against a poor forecast, and it's often just to show, the effectiveness of your current method. Another thing is, if you're looking at an application, and many of the papers we reviewed were part of an application, the forecasts are often ignored. You either use a very basic model, which and just on its own, and there's no comparison to how forecast accuracy can affect the performance of the application itself. And less than 20, a quarter of these papers use probabilistic forecasts. But perhaps one of the biggest issues is the methodologies are unclear. So it's very hard to recreate and replicate those results in those papers. And then finally, things like resolution issues, a lot of things about the data where, how far ahead you're forecasting or what sort of resolution the data is, you're only looking at sort of strict areas. So mostly it's half hourly or hourly. But if you wanted to look at things which are lower resolution, for instance, for sort of voltage control or something like that, that data is just not there. But I want to focus in on maybe one of the biggest challenges here, which is the data issues. You probably come across these problems yourselves if you're dealing with data, but often this data isn't open or it's only shared with very strict criteria connected to it. Often it's innovation data sets, so only one group of researchers can actually use it. Often it's not clear what actually data exists in the first place. So if you want to go to a company and ask for certain data, you may not be asking it in the right way to get exactly what you're after, or it might not exist in the format that you expect it to. Documentation, I'm sure you also have problems where data might be available, but the documentation isn't very clear, and it's rather impenetrable to get what you want. Licensing is another big issue, and often there's no licenses attached to this data, and it's not clear what you're allowed to do with it. And there's lots of other issues there. A colleague of mine in the energy systems catapult, Richard Dobson, did this energy data review that you see on the right. If you want any of the reports I mentioned, a lot of them are on our websites, which was looking at the current landscape. And this led into some other work, which the Energy Data Task Force, which I'll talk about later. But before I do that, I just want to mention then we also found a hell of a lot of problems with data in our review paper. So first, we found that only about a quarter of those actually used at least one openly available data set. So in terms of replicability, again, we're going to struggle. But of those papers, almost over 40% of them used a single data set, the Irish data set, and then a few used some other common ones which haven't been quite as used as much as that. But as you can see, Irish data now, and I myself have used it, it's now over a decade old. There's only 2 years worth of data there. So if you have strong seasonality there, that might not be sufficient. And obviously many of in the trial were also subject to interventions. In this case, there was many who were, I believe, there for sort of new tariffs were tested, I believe. And then obviously they're not necessarily a true cover of all the demographics. I believe most of the households there were sort of 3 to 4 bedrooms. If you're interested, we've also put one of the authors has put a page together which has a list of LV data sets which might be useful in research. So hopefully that's useful. Okay, so yeah, then given all these problems, the Energy Data Task Force was launched. So this was set up by government and led by the Energy Data Task Force, and Laura Sandys was chairing it. And the idea was to try and understand what are some of the barriers, to getting data out there, and what are the needs and requirements. And so they came up with five main recommendations. And this was this report was released in 2019. And so there's been a lot of work in that area since then, which I'll get onto. But essentially, there's 5 core recommendations. One of them was just simply, digitalization of the energy system is quite important in this respect. So getting new monitoring out there, always improving the systems you have in place. But then there was 3 sort of building blocks, which were mainly about making sure we could collect data, collect it in the right way, make the access proper, and proper governance and that sort of thing. So a data catalog was recommended, an asset registration strategy, and a digital system map. So this idea essentially of almost a digital twin of the UK energy system. But one of the primary outputs from this was the presumed open data principle. So the idea behind this was to sort of, let's start from a place of saying, let's presume data is open. And if it you can't make it open, and there's lots of good reasons why you shouldn't have it open. They could be commercial reasons, they could be security issues. Then maybe you can release it in a different form, or perhaps you can do some redaction. You can maybe aggregate it, apply differential privacy or something like this. But it might be in the end that there's nothing you can do, and it simply just must be a closed data. So if you start from this presumed open data principle, though, and then you triage it, you might get a lot more data out there than you would have otherwise. And then there was I'll just mention quickly one of the other recommendations, which is the data catalog. So the idea behind this was to sort of have a sort of standardized metadata, which you could collect all the available data sets, whether they're open or maybe not, but you could at least request access if they weren't. And again, depending on data triages, that data might be released in different ways. And it creates sort of a data catalog for all the the data out there, and it helps obviously support innovation and so other researchers perhaps out there. This slide is just sort of showing that there was a very positive response when it was first launched, from across the energy sector in the UK, and a lot of things were implemented since then. So in particular, I'll talk about a couple of these, but the main one here is the energy data visibility projects. Icebreaker One have been involved in a lot of this work, and one of those was creating this open energy platform, which sort of focused on a data sharing ecosystem, proper governance, licensing, and authentication, so you could access that data. And also the Energy Data Visibility Project, which was generating that data catalog and a search engine, so you can search for that data. And we've also been involved in a few things to support this work, especially through the Modernizing Energy Data Access program. That's included looking into sort of energy data glossaries. My colleague looked into that, and also looked into energy data use cases. And the report by Emily Ainsworth should be available on our website. And things like data interfaces and APIs, and how you can help support access to data. Okay, so I think this might be one of the last things I talk about. Essentially, the presumed open principle was there to sort of help improve getting the most out of data. So how can you increase the value of the data that you release? One sort of small aspect of that was to design some data science challenges. So we set up a project with Western Power Distribution, who are one of the major DNOs in the UK. And the idea was to sort of do two things: maximize the visibility of data. So we helped them with their data cataloging, and also maximizing the value of data. And one way we wanted to do that was to sort of set up a data science challenge where we could uncover things about the data. We could look at how we could do proper benchmarking. Maybe this could come out with techniques that are better than others. What are the best ways? What data is some of the most useful? How much data is needed, and that sort of thing. So we created this challenge, which ended in about March this year. And we ran it over 4 weeks and the practice challenge. If you ever set up a challenge, I would recommend a practice challenge. It helps to iron out a lot of difficulties. But the thing is, the prize is, there was no monetary prize involved in this. We were just hoping to release some interesting data, and the problem would engage a lot of people who were interested in getting that data and also tackling an interesting problem. So I'll just briefly talk about the scenario. I won't go into details of the actual challenge itself too much, but essentially we looked at a battery, which we sort of positioned in the southwest of England, where there's a lot more sun. And it was also connected to a 5 megawatt solar farm. And the idea was to design to control a storage device, which would support the network by doing two things. It would reduce the peak in the evening, and it would use as much solar photovoltaic PV energy as possible during the day. And we do that for every day of the week. Now, of course, there may be some realism issues here, but the point here was we were trying to make a well-defined problem which could sit well within a challenge environment. But if you want to frame it in sort of a mathematical language, what we were essentially asking the participants to do was solve a constrained optimization or control problem under uncertainty. And the uncertainty here is obviously the PV generation and the energy demand. I won't go through into the scoring. Essentially, the scoring element was made of those two components: what percentage peak reduction you performed, and what was the proportion of energy stored in the battery. as sort of an example here, here's a week-long data, and what we've done is we've shown the final profiles for the grid after implementing two different algorithms. One is a perfect, so we assume true future knowledge, and one is a naive one where we assume last week was exactly this week. So you can see the reduction of the peak in the evenings, but also you can see we've increased the peak in the daytime. So here's where a bit of realism has perhaps been lost. But the main thing I wanted to highlight was just the engagement we had. So, despite there was not a large monetary prize, but it was an interesting data set. We released, PV generation data, we released demand data and weather data. We got a large amount of interest, and, a large proportion of these individuals. In the top right, you can see who stayed with the challenge in blue. Pretty much everyone who started from the practice challenge onward, finished. And this was a lot of work. These were people who were working full-time jobs and doing it in their spare time, or and it was also academics and consultancies and industry. And so we had, I think we counted in the end, it was about 72 different organizations, institutions in the end, and 30 of those institutions were universities. And a second thing which was quite nice was that a lot of people were tackling these problems for the first time. But they improved a lot as the challenge went on. So, starting from the practice challenge, we're only sort of 26% beat the benchmark. We were getting to almost 2/3 of the individuals were now scoring better than our benchmark that we provided. So yeah, the summary points to that essentially are, the interest and value, which I mentioned. But I think another thing was that it was so interesting to see so many different people using different methods and approaches, different ways of extracting features for the models, different model types in general, from machine learning type ones to statistical ones, and people using sort of point models to probabilistic models and that sort of thing. And despite that range of models, the top 5 teams all did very well. I mean, you'd be hard pressed to prove that they were statistically different from each other. So there was no perfect method or approach. If you're interested in the approaches, there is a video of the final competition, the top 5 individuals, participants, teams, if you're interested in that. But another thing we were hoping would come out of it, there'd be ideas for benchmarks, and perhaps we could actually even set some sort of state-of-the-art definition for these types of problems. If you're interested as well, and I can send this around if you're interested, we are setting up some new challenges in just a month or so. So yeah, please take part if you're interested. I guess I could finish on this slide so I don't take up much too long. I guess the final points I'm trying to say here is, the data is going to be very essential to driving innovation, but I think it needs to be across the sector. You need industry to be willing to release that data. You need the regulator to set the right, rules and make sure that everything's done in the proper way, in a secure way. And academia also needs to be, willing to support the wider sector as well. I think one way that academia could support is by investigating, how to include more privacy protection. That's one of the big blockers sometimes, or at least one of the fears of network operators and suppliers, is that they're worried that they'll be releasing some personal or private data. So perhaps there's ways to look into things like, differential privacy, create tools for that. And I guess so a few things here are just from almost from the review, but there's some things that would really help support the area a bit more. I think validating the research against more open data sets, hopefully open, will help to sort of strengthen and understand what methods are working. It would be good to also compare against existing methodologies as benchmarks, rather than just comparing against, maybe a weaker version of the model that's being tested, or perhaps even just nothing in many cases. I do believe that if we're looking at the low voltage, that we need to move towards more probabilistic. Things are too volatile there to really measure the risk that's involved. And certainly if you can represent the risk in a good way to network operators and engineers and the industry in general, I think they may be more confident in applying some more smarter methods. And finally, yeah, if the application is a big part of the research, then it's very important that the forecast accuracy is explored a bit more, because it is often neglected, and it means we can't really assess what's important and how much attention we should spend. If an increase in accuracy of 10% has huge an effect, then we should explore that. But if it has a very small effect and more effect is on, say, the control aspect or the other model that it feeds into, then perhaps we need to actually understand that so we can spend our time wisely. Okay, I'll maybe skip this very quickly. Okay, I'll very briefly mention this. So data science skills is one that's an area of concern across the sector. So we have set up a survey. So if you're interested and people in the energy sector who employ data science in their work or are interested in doing so, it'd be really great to hear their opinions. So I'm happy to send this link around later if it's of interest. But it'd be great to get some input if you know anyone in the energy sector who'd be interested in helping us out. And that's it from me. So I guess what I'll do is I'll pass on to Professor Grundrod, who will take us through the next part.
Hey, thanks very much for that, Steve. Can everybody see me and hear me all right? Yeah,
I can hear you.
Yes.
Okay, that's good. All right, Steve, why not put that link up on the chat, in the chat box? Put that link up to your survey, and then anyone sitting on the call can just grab it from there.
I will do.
Yeah.
We can also put the link of the challenge information in our website.
Yes, excellent. Yes, please do that. Okay. Well, first of all, thank you very much indeed for asking Steve and myself to come along and talk to you today. For me, energy and energy use, particularly in the low voltage end, in the citizen, the consumer, the domestic end, is very much a big B2C operation. And it seems to me that there's some learnings that come from other sectors, such as Wi-Fi, mobile phones, online retail, leisure, media consumption, online finance, and all that sort of thing, where we've seen two big paradigm changes. One is all of those areas have become like energy. People just expect to plug in and turn on 24/7, anytime, any place, anywhere. And of course, energy has always had that. And so it's developed a culture, a kind of engineering, distribution and supply culture of being very proud of the fact that, the lights don't go out and things like that, the systems actually work. And but arguably, they don't have a culture of being customer centered. And what I mean by that is that years and years ago, 30 years ago, if you went into an American retailer like, Walmart or Super Value or H.E. Butt is feed in Texas, I know that much. If you went into those companies, they would be very proud of the way they distributed product and put it onto the shelves. And so you didn't walk in and there was empty shelves. And gradually over the years, as they've got more data, they've switched. So now they're more concerned not just with putting things onto the shelves, but why customers ever take them off the shelves. Why do people demand certain products or services? How do they demand it? How can they compete better to meet those demands, and so on? So this customer-centered nature is something that has been picked up, as I say, with retailers, with media, with finance, and we've been relatively slow to it in the energy sector, perhaps because we started with this other culture of, quality of performance and quality of supply, being supply centered, being distribution centered, instead of being customer centered. And I think it's good for all of us who work in this area on the technical side to reflect on that. This paradigm change hasn't taken place really so much in energy. And yet, ironically, that's always been a 24/7 game. And whereas these other sectors have come in and become 24/7, actually they do it in a much more customer-centered paradigm. So why is this important for those of us who are interested in data science and analytics? Well, it's important because, as Steve said, the digitalization of all these networks, the power that data can give us, offers us the power to flip from being supply and distribution centered to becoming customer and demand centered. And that's the change that's going to take place. And this will take place whether the distributors and the suppliers like it or not, because the whole customer relationship management thing from suppliers will be contrasted in the minds of their customers with the sort of customer relationship management they're receiving from Spotify, from eBay, from their banks, from their mobile phone operators, and so on. So really, the energy sector has to really raise its game in terms of its customer centricity, and it has the data to do so. Does it have the vision and the leadership to do so? It's just not obvious. And in the UK, I would say there's been a lot of talk about distribution network operators, instead of being like, managing the motorways or the autoways, the auto routes, actually they have to become more like air traffic controllers and making sure they can create capacity for people to do what they want to do. And largely that's talk, I think. And so we need to actually exploit the data to enable that change, and then new products, services, new types of tariffs that encourage or discourage certain types of behavior will come forwards. Now, if we take this digitization and the increase of new technologies, whether it's PVs, whether it's electric vehicles, whether it's heat pumps, whatever it's going to be, we have new forms of storage. Maybe we're switching our generation from old-fashioned power stations to more sustainable sources, as long as the wind keeps blowing. These are big challenges to us, but if we can just merely reinforce the existing behaviors amongst customers, then the companies that we're working with will have missed the big opportunities. They'll have missed opportunities to reduce total energy usage. They'll have missed opportunities to reduce the relative costs, particularly to low-income customers. Very well-paid university professors like me, we can pay for our energy. It's not an issue. Okay, but at the low income end, where people are already in energy poverty, that's got a technical definition. I'm not sure if it's the same in the States, but we have a definition for people who spend more than X% of their household income on their energy bill, and that defines them as a sort of living in energy poverty. And increasingly, they'll be missing out on opportunities to create new products and services. Why would they be able to create new products and services? Well, it's because of people's behavior. Remember, we're supplying a fairly vanilla product, which is energy, electricity. We're supplying a product which doesn't really differentiate itself. It's not consumed with a brand attached to it. It just comes through the network and is used. And that capacity, that supply enables people to do all sorts of things in their lives, good things, bad things, whatever. It enables them to get on with their lives. And so a great first question in this sector is fundamentally, how many distinct types of customers are there? How many distinct types of domestic behavior do we see? Now, if you asked a sort of planner, they'll say, well, we've got, 8 profiles, and when we get a new housing development, we assume we've got a collection of those profiles, and we work it out, and then we multiply it all by 2 and make sure we can meet that demand. That's what we do. And so for them, they're 8, and they know what they are. And when you show those people the actual profiles of domestic consumers' behavior, they are shocked the first time they see it. They say, no, there's no way people are doing that. No, I don't believe it. Because the planners have never really had to live with the operations. Similarly, if you talk to the marketing people are obsessed with spending their budgets, because if they spend their budget up, then next year they'll get a bigger budget. So their main performance target is to spend their budget, right? There's no ROI calculation, no quality there. That's marketing for you. Okay, but actually, if you said to them, well, you know, how many different types of customers have you got? They wouldn't really have a clue. If you're saying, where do you get your best customers from? Do you acquire them? Do you just have to go and find them and be competitive for them? Or do you grow them? Do you build loyalty and constancy and have good customers? And eventually they grow into being even better customers. Because remember, the company's paid by the area under the curve, not by the current rate. It's paid according to the area under the curve going forwards. So here's an example. 10 years ago, when Steve and I were first working together, I think it was about 10 years ago, I'm not quite sure, but we first gained access to sort of domestic smart meter data. And this was half-hourly data where we could see the energy use for every half hour, day after day after day after day. And we would split it into weeks. So we'd have 48 half hours by 7 days a week. And that grid, sort of 48 columns and 7 days in the rows, that grid tells me what one particular customer was using for that particular week. So the fundamental object of interest is the customer week, the consumer week. And of course, when you look at that by eye, you can see that there's a lot of strange stuff going on. And there's also a lot of obvious things going on. People behave differently at weekends than during the weeks when the kids are at school and they're at work. People go to bed early, or other people go to bed late. If we look at, say, a household where there's just one or two seniors living, every day is the same. Yep, we're all going there. Every day is the same and not much is happening and the costs are fairly low. And if you look at other households where there might be a lot of kids, or, you know, once they're out of school, everything's on all of the time, all day, all night, all weekend. Welcome to my life. The other thing that we learned very quickly when we looked at households that were, say, in adjacent properties, that people are not like their neighbors. Energy is consumed privately. And so you can't look at, say, 5 or 6 similar houses down the road and figure that they've got similar profiles. That people have their own economic constraints, or people have their own behavioral performance and desires and things like that. And you know, never before has their consumption of energy been visible in a way that perhaps which car they drive is visible, or which brand of makeup they use, or anything like that. But, you know, so one way of thinking about this revolution is for energy consumption to become much more visible. And of course, we're seeing that in the UK with the move to hybrid cars and the move to electric vehicles, where for those who can afford them, there's almost an element of keeping up with the Joneses. And this of course presents its own problems. I'll come back to that in a moment. So a central question is, you know, how many different types of demand profile are you actually dealing with? What do you mean by a type of demand profile? Well, one way to deal with this is to use something like finite mixture modeling. And if you don't know what it is, Google it later on and have a look at finite mixture modeling. You'll probably run into something called the EM algorithm. And the EM algorithm is like clustering for grown-ups. The beauty of it is it doesn't just use real numbers, it can use categorical attributes, or it can use binary flags. And basically a single class is defined by a distribution over all such attributes. So you might have some attributes that are reals, other attributes that are integers, other attributes that are categoricals, and so on. And you just have a distribution with some hidden parameters, which defines a distribution over those things. And then you imagine that the whole distribution of everybody's consumption is a finite mixture of a finite set of those component class-based distributions. And then, of course, you need to set about finding what those could be, because we just see household weeks, and we don't see the latent variable, which is the mapping from the household week to the class. We just don't see that. And the EM algorithm is a great algorithm that responds to that. And if it's reals, it'll be using Gaussians or multivariate Gaussians or Poisson distributions. And if they're categoricals, it use some sort of multinomial type distributions and things like that. And there's also all sorts of little tricks and spins, whether you like to use tricks that mean that you're never actually predicting zero probabilities for anything. That's always kind of quite good. Laplace's law of succession is your friend then at that point. The downside is that you kind of have to specify the number of classes that you're looking for. It's a bit like other clustering algorithms. There are algorithms where you can just let it go, and it gives you the number of classes is a penalty, like the log of the number of classes is a penalty. And so then it will come down to saying, well, it suggests there are 52 types of customer or something like that, and that's the best number. But actually that isn't very helpful, because the marketing department and the planning department and every other department doesn't want 50. They can't manage 50. 20 is quite good, because then you're roughly down to 5% on average of each of the consumer population within each class. You don't really want any ridiculously large classes either, and you only want small classes if they're really super extreme and things like that. So we as the data scientists are going to have to make some good decisions. There's no way the marketing people or the planning people or the operations people can get involved in that discussion. And we're going to have to make those decisions. And they'll trust us on the maths, but we won't help ourselves if we come up with sort of really strange results that says, well, there's 150 different types of behavior we're seeing, because they can't manage that. And we shouldn't be anticipating that they could manage that. So typically we choose suitable numbers of classes, bearing in mind the sort of applications that we got in mind. And of course, we see this in these other B2C areas, where quite often they'll have, 10 classes of customers to report at the board level. But then when they come to operations, they'll break each of those 10 into 3. So they'll end up with 30 or something like that. So they're down to about 3% of the entire population or something like that in each one. But for board presentation purposes, strategic purposes, they'll talk about a division into 10 segments. And then, of course, we can see how customers' behavior changes over time. We can see if they sit in the same class of behavior, or whether they, move around and become bigger users or lower users as the season changes, as the weather changes, or as people come to stay at Christmas and all of that kind of thing. So we've made the customer week the fundamental currency here. And we've sought to answer the question, how many customers have we got? And then we can look at each customer and figure out, well, what is the best way to communicate with those customers, or what's the best deal for them? Can we create some deal for them which is better than the one we've got, and build some loyalty and things like that? And of course, this is an opportunity. As I said before, you'll tend to find the marketing departments of suppliers are quite resistive to this, irrationally so. And it's because they see some of their budget slipping away into something called data analytics and data science and AI, and they don't like it. Because it's a mystery to them, and they haven't got to where they've got to today by being nice to data scientists. They've got there by their own brilliance. So we have to tolerate that as data scientists and analytics people. We have to tolerate some of that we might do brilliant work, but there's still a kind of strategic job to do in terms of winning hearts and minds within companies. Now, there's one company I work with in Germany is called E.ON. So E.ON sell energy all over Europe and in the UK too. And the headquarters is in Essen in Germany. And they are such a company that's going through what they call a digital transformation, which is where they're going to go. And they say they're going to go all in. They've got rid of some of the businesses they had in generation that they didn't want anymore, and they're going all in on the customer. Okay, this is we're seeing that paradigm I talked about at the beginning take place. And of course, it's being driven by their data science group. And they've got everything there that we've talked about so far, and including psychologists. including social scientists in those groups. And I think that a permissive view of data science is that where we're dealing with customers, where we're dealing with customer weeks, we need to understand the motivations for behavior and behavioral change. Of course, when smart meters came in the UK, there was very little behavioral change achieved by the smart meter. Basically, we just saved the cost of people having to read meters. There wasn't this big push towards understanding behavioral segments of the market that I've just talked about, say using the EM algorithm or any other unsupervised discrimination algorithm you like. I'll come back to black box algorithms in a minute. So yeah, these are very big strategic changes in the business that will take place, and actually the companies that don't recognize they're taking place won't be here in a decade's time. They'll find that their business has gone elsewhere to people who took the data and used it to drive a strategic data transformation. So a few things to check out there, but if you look for finite mixture modeling or the EM algorithm or any other ways, you'll find a very transparent way of doing unsupervised classification of say, customer week consumption behavior. And of course, you'll see, in order to do that, you need to have certain attributes that you extract from that raw data. You might as well help the algorithm. And so part of that could be to look at base load consumption, which is stuff you do every day, all day, you do all days. So, it's the sort of common denominator of use. And then there'll be what you might think of as discretionary things. Like, what time do we have dinner? We're going to have dinner, so we're going to be putting the cooker on, or we're going to have a bath, so the water's going to go on. But some of that is discretionary, and so that can move. It doesn't have to be at the same time every day, but nevertheless, some things do, because the school bus leaves at a certain time, the same time every day, and so they're subject to externalities or subject to cultural or economic constraints. So you'd look at time of day biases, you'd look at day of week biases, you'd look at the base load versus discretionary loads, and then really importantly, you'd look at some measure of the consumer's volatility. By which I think, rather than take a technical definition of volatility, let's replace it with forecastability. If we had our best forecaster, could we forecast this customer? If we could, then we can manage their demand in the sense of, maybe using local storage or something like that to rule out the peaks. But if actually you've got a customer who's chaotic, who's doing mad stuff every day, all of the time, and consistently, and there's just it's completely like white noise, their consumption of energy, then nobody can forecast that. And that's the customer from hell as far as a low voltage network is concerned. And most of us live somewhere between those two extremes. And that's why we need to know how many different types of customers have we got. And remember, when you show these data-driven profiles to planners, they'll be shocked at the sheer dispersed nature of behavior that they're actually planning for, because in their world, it's been a lot easier. So there's also a question of whether the consumers themselves would even recognize their own behavior. I don't think this has been really bottomed out, but it's a really good question. If I talk to people and show them, oh, this is the group of people you're in, would they even recognize they were in that? They did that sort of behavior. And that affects the sort of customer relationship management. It affects the marketing, but we're beginning to undermine the authority of those customer marketing professionals within those companies. Okay, I mentioned forecasting a couple of times, and Steve did too, and he talked about their review fairly recently of forecasting challenges. And I just want to talk about one aspect of that where we worked together for a while a few years ago. And this is where we're interested in general of forecasting spiky data. You've got big spikes when people suddenly turn stuff on and add loads in the home. And so we're in general in the realm of forecasting spiky data. And by its nature, if you attempt to forecast spiky data and you just happen to miss the spike, you get penalized twice if you're using an absolute metric. If you're using, if you define the errors as actuals minus forecast, then there's going to be a positive spike and a negative spike. And so the error thing will penalize you twice. So you might have been better to have forecast no spike at all, and then you'll only be penalized once. Well, this is crazy. Okay, so you need methods in forecasting that forecast spikes, and if possible, forecast the spikes early. So if they're in error, I'd rather that I forecast a spike early, so I was ready for the actual when it comes after, rather than forecast a spike later, where I was sitting there happily doing something else with energy, charging up a battery, and then an early spike comes and hits me. An early actual spike comes and hits me. So if you think about it, if you're in the business of forecasting spikes, you need to be forecasting the spikes early so that you can have an early warning of a spike that's about to come. And one of the things we did was show that it was possible to set up time warping. So you could take a forecast and you could warp it a little bit and push the spikes back and things like that, and see if you could match it to the actuals. So low cost time warping. Obviously, if you're warping it a lot, then there just needs to be a cost to that. And but that way you can build methods which forecast spikes. They look realistic and they err on the early side. So the forecast spikes are usually a little bit ahead of the actual spikes. And so this would give us a lot of confidence if we were controlling, say, energy storage within that facility, within that home, that we weren't, relying on no spike while we just charge something up or something like that. So the forecast and control applications really demand that you forecast spikes and you forecast spikes early. I'm not going to say anything more about that, but there's a paper by Steve and myself and others in the International Journal of Forecasting, volume 30, issue 2 comes to mind. And the problems addressed there really get to the point of how to forecast spiky data. This is a known problem in other areas of forecasting, and so warping has been sort of thought of before, and it's not unrelated to the sort of earth movers problem. Some very classical problems in mathematics, for which there's huge interest in data science these days. Okay, so forecasting is a big issue. Community storage solutions. I'm quite keen on these. This is where you might have, one big battery and a block of apartments or something. Not everybody has got the space for a battery, or it wouldn't be safe to distribute batteries through apartment blocks or something like that. But you could have a very big battery, and the aim of that battery is to kind of mollify the total demand of that apartment block on the local network. Of course, the battery can charge itself up at off-peak hours, so putting a burden on the local network during those off-peak hours. But then during the on-peak hours, citizens can draw energy from the battery rather than the grid. And so we've changed the profile of a whole block of domestic users all at once. And of course, the battery will make some money because people are going to be billed by what goes through their meters, which is sort of inside their front door. But actually, not all of that energy has come from the network. Some of it's come from the battery. So when the accounting's done, the battery will have sort of effectively have to receive money back from all the suppliers who have the citizens as customers, because they've charged those citizens for energy which they haven't actually supplied. It came from the battery instead. But of course, the battery has to pay for the energy it used overnight, say, or at low cost times. And but there'll be a net profit for the battery because it receives these rebates from all the suppliers. In fact, if you were a supplier, you'd probably install the battery yourself and do everybody a favor, and the supplier could own the battery. That'd be fine. But there then comes a couple of ethical and rather intriguing problems. So the battery makes a profit, and everybody's paid for their energy as if it came from the grid, which it didn't. Some of it came from the battery. So how do you then distribute the money across all the people living in the apartment block? Well, one way would be to just look at the amounts and time of days and stuff like that and just give them the money that they should have when they're using battery over. But actually, that's not very wise, is it? Because you would just sort of end up giving most of the money back to people who had the biggest usage. And so really, you've only produced a solution for the heavy users, and the poor old couple, the seniors, they're not really getting any benefit from this. Wouldn't it be better if we rewarded good behavior? So remember, the battery only makes money because people's behavior is forecastable. Supposing I move out of the apartment block and another family, say Steve's family, moves in, and they're just white noise demand profile. They're the people from hell who've moved in, and they use so much energy that the battery can't make any money anymore. So everybody loses out. So we ought to punish such people for coming in and spoiling the cozy relationship we had between our energy bills and the battery. Except we don't really know how our neighbours are consuming energy at the moment, and people would have to sign up to such a scheme. But clearly, we'd be in a position where we could fairly reward people for being predictable, for being forecastable. Would that be acceptable? And how would we allow people to interrogate that? And clearly, if we find that one family moves out and another family moves in, and then everybody loses money, what's the implication of that? So there are some difficult problems there, even when we can show as data analysts that we can actually do this. And I think we're very close to being able to do that. Customer behavioral journeys. So here we've got people moving from class to class of behavior over time, hopefully becoming more responsible users of energy, especially if their energy use has become visible and transparent and things like that. This is the realm of hidden Markov models. Again, there are latent variables called states, and people are moving between those states at given rates. There's a transition matrix, all this stuff we know about. Okay, and to do this, you need some modeling. You need to be a mathematician or an engineer or a physicist. You can't do this if you're coming in from other disciplines, and because there's some delicacy to these algorithms. Let me talk a little bit about black boxes versus transparent methods. So transparent methods are ones where we as experts can go in, we can see how it works, the EM algorithm, we can see what it's doing, the hidden Markov modeling, we can see what it's doing, the forecasting I talked about, we understand how that time warping can work, and it's completely transparent to experts. We can see how that is. It's never going to be transparent to my mum, but it's certainly transparent to the PhDs who are running this program. But then there are sort of machine learning and deep learning algorithms, and this is popular because that's become popular everywhere. But actually, we need to take care, because we need to work in areas where these algorithms that we're using for public consumption of energy are much more transparent, and people have a right to ask why they've been allocated to classes or not, and things like that, and why somebody else is being offered a different deal and they're not being offered that deal, and that sort of thing. And that's going to be very difficult to justify. There are also problems with spoofing, and you see a machine learning algorithm, it just looks at everything it's given, and we don't know where its sensitivities are. And recently there's been a lot of work in the UK where we've sort of started to look at semantic perturbations for things going into AI algorithms, black box AI algorithms. We're treating them as a black box. They more or less are a black box because we don't fully understand what the thing's responsive to. And everybody's got their favorite paper where they can see machine learning applications being spoofed. In actual fact, there's a mathematical theorem that says as the dimension of the objects you're considering goes up, the probability that you can be spoofed goes to 1. So this is inevitable as we put more and more sophisticated data objects into ML and DL packages. And so we need to be very aware of that. And the idea of semantic perturbations isn't that we just produce little perturbations, that we normally, when we talk about perturbations, we really just mean shaking the real data a little bit and looking to see if the result is stable. Okay, I don't mean that. I mean actually making quite large perturbations which are operationally realistic. So whatever that means in your context, I'm making quite large perturbations which produce data objects going in which are operationally realistic. And a human being would say, yeah, but that bit of information isn't really part of it. That doesn't really matter. But the ML, the DL, doesn't know that. So there's quite a bit of work at the moment thinking about not the question, does it work? We have an ML procedure, we have an AI procedure, and we're not just asking the question, does it work according to a restrictive set of performance criteria? We're actually asking the question of when will it fail? Under what reasonable circumstances can we make this fail? And that's a very different question. So as a result of this, I've been, recently writing something called unconventional AI. And conventional AI are methods and problems and applications where we can kind of achieve a consensus between experts that this is a good idea. If we put in a research proposal to our bosses in a company or in a university, or we put in a research proposal to public funders or something like that, then 5 reviewers would review it and they'd all say, oh yeah, this is a good idea. But in truth, those sorts of applications are really in very well-defined areas where there's a consensus. They're improving things within the current paradigm because everybody's agreed that this is but supposing you have a proposal that you put to an energy company or to a public funding organization, and the referee comes back and says, well, this idea flies in the face of the last 10 years of research in this area. We know where we're going and we're not going in this direction. But other reviewers say, well, yeah, this would be amazing if this could actually be pulled off in some way. They recognize the vision. And what I'm saying is that we need such unconventional ideas in research programs. They don't have to take up all of the resources. Maybe 25, maybe 30% of the resources should be unconventional, big change, big game changers, big disruptors, paradigm changers. And then the other 70% of the spending and resources can be put down to improvements within the current paradigm. Let's call it conventional AI, which achieves a consensus. Whenever we show it to 5 experts, they all agree, well, yeah, this is a good idea and it's a good next step. But actually, we've now got to the position in the UK, and I'm sure it's similar, that the curse of peer review has meant that many countries like the US and like the UK have now sort of engineered away the upside. We've engineered away the risk. And although we've got data scientists who want to do really radical things, we're not funding those things in the right proportion. Some of them are just luckily getting through, perhaps based on the reputations of the proposers rather than the details of the proposal. But we need to rethink this, and we need to get much more unconventional innovation into the use and abuse of data science. This isn't just for energy, of course, this is across a load of sectors. So I started to write about this last year, and there's a paper up on ResearchGate on unconventional AI you can all read. And this applies across a very wide range of sectors. So I don't think it's something that that we need to spend too much time on now, but it's certainly going to affect all these customer-centered sectors, and actually the winners will be the ones taking the bigger risks. And so it's crazy for public funding to all go into conventional applications and conventional methods where we can all agree this is a good way to go, this will probably work. It's been, a lot of these proposals have been de-risked before they've been written down. because people have done all the preliminary work. So we're just not getting our fair share of unconventional AI. Okay, I'm going to stop there, but I hope some of those sort of strategic level things are of interest to everybody, and particularly if we look for the sort of changes, these paradigm changes we're going to get in the energy systems sector. Thanks very much. Have we got any questions?
Thanks, Pete and Steve, for the wonderful talk. We got some questions, and let me find the first one. Yes, the first question goes like this. Would the following two-step method help to improve the forecasting accuracy? The first step is to identify what loads exist in the house first. Then we can do a conditional forecasting. Will that help?
What do you think, Steve?
Just a minute, I'm muting myself.
That's good.
I mean, I guess what you're asking there is about learning behavior within the home, you know, sort of knowing about what's in the home and then doing a forecast. I mean, sort of like more bottom up forecasting. It's a lot trickier. There's a lot more data required to do that. And of course, as we get more, maybe more appliances modeled, then in that case, you know, there is possibilities, a lot of research to do in that area, and there's a lot of people have looked at NILM, sort of non-intrusive load monitoring. I think in terms of, you know, there's probably easier approaches to do that sort of stuff. And I think with smart meters around, that's probably, I think a data-driven approach is probably, you know, as Pete was talking about, was probably the way forward for that at the moment. As you know, we know that houses that might be similar to each other, maybe even have similar appliances, won't necessarily have the same energy behavior. You're not like your neighbors, I guess, as Pete says.
The other problem is you need much higher frequency data in order to do, you know, there is some work in the UK where people are looking at, oh, you know, I don't know, when the kettle goes on, or when, you know, the different loads in a house, and they could probably do that by monitoring data more intensively in the house. You can't really do that with half-hourly cumulative data. Personally, I think that's a red herring. I know some people are probably working on those areas, and it kind of fits in with these, you know, websites where you can, you know, monitor your own use and things like that. But, you know, how many times do you want to say, you know, you've got to turn the electric blanket off? How many times do you want to be told to turn the, you know, the washing machine off, or the dishwasher off, or things like that? We know those things need energy, and we, you know, some parts of people's lifestyles simply aren't negotiable. So I regard a load of that as being really quite unhelpful and missing the point. The point is that there need to be different kind of inducements in tariffs to encourage different sorts of behaviours, and we haven't seen the development of those for the time being. So I accept that people do it with high frequency data. I don't know what the ROI is on it.
I see. Thank you. And the next question is probabilistic forecasting really implemented in industry, or still mainly the theoretical research? I feel that most utilities still use point forecasting.
I think you're probably right in terms of it's, you know, the energy industry has been relatively slow to pick up some of the more advanced algorithms. From the companies we talked to, I think they are looking at these things now, and they're very interested. It's one of the things I didn't really mention too much, just briefly at the end, was the data skills gap in some ways. So it's having the right people who can implement them. But there are certainly companies like the National Grid in the UK, and I guess they're also in the US, are looking at probabilistic methods now, especially for wind forecasting and supply and demand. And they understand now how much more volatile the system is. They're going to have no really choice to do that. But I'd say that certainly those people who've been data driven from the start, like National Grid, I would say that they are, you know, are looking at, certainly for wind and solar, you know, and their demand forecast.
I see.
Pete, do you have a perspective?
No, I think that's exactly right. I think a lot of the companies involved in the energy ecosystem need to up the game here, and that's probably skills limit is the biggest factor there. Also, their mindset, which is still, focusing on supply rather than demand.
I see.
Yes.
The next question for Steve. You mentioned the open energy platform.
Yeah.
Is that some NGO for the open source data or free access data source?
It's not.
What's that?
Yeah, so it's a platform, UK-based platform. So it's trying to collect as many energy data sets together. I guess I should maybe share the link to that. It's still in an early stage as well, but it's not necessarily open data as well. It's also telling you where certain data may be, which you can access if you had the right, membership, if you will. So they're also running a membership model, which, says you could actually access certain data if you've signed up to a certain agreement. So really, they're running two things there, as to say, the governance platform as one aspect of that. Maybe I'll share that in the link so that you're welcome to use it and try it out, because it's in a bit. I think it's in a beta stage now, if I understand. But they're also looking for new data sets. So if you find any more, just send them a nudge.
Okay, it seems to me that it's like a company. There's a company called Pecan Street in the States. I don't know if you know that company or not. They are like also providing some data sources. Yeah, it seemed to me that a similar platform.
I think that was picked up actually as part of the review. We linked to some of those, but it seems sometimes the data may change, which is available or not. So I think at the time of writing, some of that data is no longer available.
Okay. Yeah, and I have a question. So for the final curve after the demand response or valley filling or curve valley filling, for some valley filling curves, like what is the ideal demand curve? You show some like a peak shaving, right? Then to some spikes are filled into the like a valley, right? And you smooth the curve. What do you think is an ideal curve that I mean, you can feel it to some other valleys, right? I saw that in the beginning you have a very low valley. You can feel it there. You can also feel the peak to somewhere else. So how can we define the ideal demand curve, right? We have to have a target, do we?
You mean here for forecasting the demand curve, or well, I guess, I mean, the part of my answer is sort of there's what Pete was mentioning with the spiky forecast. Predicting that can be very difficult because we can't measure it correctly. Having the right measures is really key to that. And there's a payoff there. The other side is it's probabilistic, but perhaps that's quite computationally expensive. And to do that and implement then a stochastic control optimization is two levels of challenge there, I'd say. So, well, what is an ideal curve? I don't think we know enough really about what would be. That would be a very interesting question, I think. Can we define profiles which are very susceptible to storage control? I think that would be a really interesting problem to if you could identify features which would do that.
Yeah. So how do you feel, Pete? What's the ideal demand curve that we would expect?
For me, it's always sort of customer led or data led. So I like the idea of splitting up the customers into different classes, and then there'll be typical demand curves in each class, and they'll be very different. And some of those, honestly, people in the business will be quite resistive to them because they just don't imagine people are using energy like this, but they are. And so I think that the only way you could have a satisfactory answer to that question is to use the power of the data to say, this is what people are doing. 3% of households are behaving like this. I think the knock-on question that Steve sort of brought up is saying, well, which of those customers would be the biggest beneficiaries of new technologies from smart storage or something? And that's a great question, because that would allow a lot more efficient targeting of technology. You know, we're going through this thing in the UK at the moment where they're saying everybody's going to have a heat pump by 2035, which is only 14 years away. I mean, that would be great, but actually the majority of people with those heat won't benefit at all. But some people will benefit an awful lot. And of course, this is the sort of, you know, the dirty secret of greening the economy, that, you know, you do create a lot of cost in certain, you know, homes, in certain companies, small companies especially, where they're going to have to go through this process, but they're not especially going to see an economic benefit, and they have to kind of anticipate that there's a benefit to the planet and there's some sort of social good. I'm not quite sure that works if you're, you know, living in very economically challenged circumstances. But I mean, even the work to say, well, who would be the primary beneficiaries? You see, our countries don't work like that. You know, the state in the US or the government in the UK would just kind of mandate the rollout of these things and say all new houses have to have X, Y, and Z. All new developed apartments must have this. And it's not clear that the inhabitants are ever going to benefit from all of those technologies. And that kind of gets this into a bad odor or a bad situation where everybody's going to have their own favorite anecdotes of crazy stuff that cost a lot of money and they didn't see any benefit. So actually having better targeting and better case studies is the key to winning these arguments. But it probably at the cost of having one shoe fit all. So this is a policy and political question. I've no doubt that, you know, all of us on the call who fancy doing the data science would like to answer that question. But even when we answer it, whether we'll actually get a response from government or the regulator is questionable. There's no reason why they shouldn't fund us to do it, though. So, on that happy note, I'm going to have to end there. We've got a hard stop here. But listen, thank you very much for having Steve and myself along to come and talk to you guys. And get back to us if you've got any more questions or want to take part in some of the activities at the Energy Systems Catapult. We'd love to hear from you.
Thank you, Pete.
Very much. Yeah.
Thank you, Pete. Yeah, thanks a lot. And for also Steve, if you can feel free to send me the links that you shared with us. And also, and remember you mentioned the challenge competition. Yeah, I can also help
send that
you
over soon.
Promote that. So if you like, if you have any data sets that you want to share, we can share them through our PS website. Yeah, you can. We can also share some. You can, by this way, you can contribute to the PS data set. Yeah, that's yeah. If you are interested. So okay, and
yeah, brilliant. Yeah, thank you very much as well for inviting us. And thanks, Pete.
Yeah, it's almost 1.5 hour. And thank you for both of your time. And I enjoyed this tutorial a lot.
Okay, many thanks. Goodbye now.
Thank you very much.
Thank you. Bye-bye.